Now in this lecture you'll find out the distance between the centers of two circles. In the drawing we have rectangle ABCD. Side AB of this rectangle is equal to 7 units in its length. Side BC equals to 24 units in its length. Inside this rectangle we have those two circles. The center of this circle is here at point Q. The center of the circle is here at point P. Our mission is to find out the distance between the centers of those two circles, that is to say the length of line segment QP. Because of the fact that ABCD is a rectangle, know that all the four angles inside the rectangle are right angles. So those four angles are all right angles. So this angle equals to 90 degrees. This angle also equals to 90 degrees. This angle equals to 90 degrees. And finally this angle is also equals to 90 degrees. And we also note that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle ABCD, side AB equals to side DC. AB equals to 7 units, therefore DC must be also equal to 7 units. Likewise, according to the same rule, side AD equals to side BC, but BC equals to 24 units. Therefore, AD must be also equal to 24 units in its length. Angle ABC equals to 90 degrees, therefore triangle ABC is a right triangle. So we will implement the Pythagoras theorem on the right triangle ABC. According to the Pythagoras theorem, in the right triangle ABC, here PT is the version for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle ABC is AC, therefore the square of the hypotenuse is AC square. And it must be equal to AB square plus BC square. Repeat again, according to the Pythagoras theorem in the right triangle ABC, AC square equals to AB square plus BC square. So AC square equals to AB square. AB is 7, therefore AB square is 7 squared, that is 49, plus BC square. BC equals to 24, therefore BC square is 24 square, that is 576. So in total, AC square equals to 49 plus 576 is 625. So AC square equals to 625. We take out all of this equation and get that AC equals to the square root of 625, this is actually 25. So the length of the hypotenuse AC is equal to 25 units. The hypotenuse AC equals to 25 units in its length. So I'll write it down here. In the next step, we'll calculate the radii of those two circles. Actually, we'll develop a special formula for a radius of a circle that is blocked by a right triangle. So here we have The right triangle ABC blocks this circle. And we know that the radius of this circle equals to x. So we try to develop a special formula for the radius of this circle that is blocked by the right triangle ABC. And we will try to find the radius of this circle only by knowing the side lengths of this right triangle ABC that blocks this circle. Okay, so we have here rule number 1, that according to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Tangent BC is tangent to this circle at this point. We define the point of tendency as M. So the radius OM is drawn to point M, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. If BC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. We define the point of tendency of tangent AB with this circle as N. We join points O and M together, and we join points O and N together by a straight line. So actually, ON is the radius of this circle that is equal to x. The radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees. This angle equals to 90 degrees according to rule number 1. So inside quadrilateral NOMB, inside this quadrilateral NOBM, we have 1, 2 3 rectangles. The sum of 3 rectangles is 270 degrees, plus the size of this fourth angle, the missing angle. In total must be equal to 360 degrees according to the rule, then the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle here must be equal to 90 degrees. In order to complete the sum of the angles in this quadrilateral NOBM to 360 degrees, the missing angle here must be equal to 90 degrees. So inside quadrilateral NOBM, we have 4 right angles. Therefore, we relate to quadrilateral NOBM as a rectangle. And we also note that the opposite sides of a rectangle are equal to each other. That is to say, side NO must be equal to the opposite side VM. But NO equals to x, therefore BM must be also equal to x. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that OM equals to NB. And again, side OM equals to side NB, but OM equals to x, therefore NB must be also equal to x. So actually found out that quadrilateral NOBM is not a rectangle but a square because all of its sides are equal to each other, each of them is equal to x. What is the length of line segment AN? From the domain, it is very easy to see that AN equals to AB minus BN. Again, AB minus NB is AN. AB is A and NB is X, therefore AN equals to A. Therefore AN equals to A minus X. We define the point of tendency of tangent AC with this circle as S. From point A, we have 2 tangents to this circle, tangent AN and tangent AS. Here we have rule number 2. According to rule number 2, a tangent the lengths of two tangents from a common external point to a circle are equal. We have the common external point A. From the common external point A, we have two tangents to the circle. Tangent AN and tangent AS. And according to rule number 2, they must be equal to each other. That is to say, AN equals to AS, but AN is A minus X, therefore AS must be also equal to A minus X. What is the length of line segment MC? From the it is very easy to see that MC equals to BC minus BM. Again, BC minus BM is MC. So MC is BC, that is A. BC that is actually is B. BC is B, according to our definition, minus BM, that is X. So in total, MC equals to B minus X. Again, MC equals to B minus X. So we focus on the common external point C. From the common external point C, we have two tangents to this circle, tangent CM and tangent CS. And according to rule number 2, they must be equal to each other. That is to say, CM equals to CS. But CM is B minus X, therefore CS must be also equal to B minus X. According to our definition, the length of the hypotenuse AC is C. So from the drawing, it is very easy to see that the length of the hypotenuse, that is C, the length of the hypotenuse AC, that is C, it is equal to AS plus SC. Okay, again, the hypotenuse AC is equal to C units in its length, and it is also equal to AC equals to AS plus SC. AS. So from now it is very easy to see that the length of the hypotenuse, that is C, it is equal to AS plus SC. That is to say C equals to AS. AS is A minus X plus SC. SC is B minus X. So in conclusion, we found out that C equals to A minus X plus B minus X. Or C equals to A plus B minus X is minus 2X. So we found out that C equals to A plus B minus 2X. We add 2X to this equation, and we get that 2X plus C equals to A plus B. Here we'll subtract C from this equation, and we get that 2X equals to A plus B minus C. We divide this equation by 2, and we get that X equals to A plus B minus C over 2. So we actually found out the general formula for the radius of any circle that is blocked by a right triangle. So the radius X of this circle equals to A plus B minus C over 2. X equals to A plus B minus C over 2. That is to say, is equals to the side lengths of the two perpendiculars minus the length of the hypotenuse, that is C over 2. We use this formula in order to find out the radii of those two circles. So this circle is blocked by the right triangle ABC. We define the radius of this circle as R. According to the new formula, the radius R is equal to AB plus BC minus AC over 2. Repeat again. According to the new formula, the radius of the right circle, R, must be equal to AB plus BC minus AC over 2. That is to say, it is equal to the sum of the lengths of the perpendiculars minus the length of the hypotenuse over 2. So actually, R equals to AB. AB is 7, so we substitute AB by 7, plus BC. BC is 24, therefore we substitute BC by 24, minus AC. The length of the hypotenuse AC is 25, so we substitute AC by 25 over 2. So we found out actually that the radius of the left circle equals to 7 plus 24 is 31, minus 25 over 2. 31 minus 25 is 6, and 6 over 2 is 3. So finally we found out that the radius of the left circle it is equals to 3 units. R equals to 3 units in its length. Likewise, we find out the radius of the right circle here. The radius x we define the radius of this circle as x. X equals to CD plus AD minus the hypotenuse CA over 2. And again, the radius of this circle x must be equal to CD plus AD minus CA over 2. CD is 7 plus AD is 24 minus CA is 25 over 2. 7 plus 24 is 31 minus 25 over 2. 31 minus 25 is 6, and 6 over 2 is 3. So finally we found out that x also equals to 3 units in its length. The radius of this circle also equals to 3 units in its length. So I write it down. According to, we define the point of tendency of tangent BC with this circle as M. The radius PM is known to point M, that is the point of tendency of tangent BC with this circle. Whenever you have a radius that is known to the point of tendency, then tangent BC will be perpendicular to the radius MP. If BC is perpendicular to MP, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. We define the point of tendency of tangent AB with this circle as N. We join points P and N together by a straight line. Pn is the radius of this circle, is equal to 3 units. The radius Pn is known to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NP. If AB is perpendicular to the radius NP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. So inside the quadrilateral NPBM, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. Only to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside quadrilateral NPBM, we have 4 right angles. Therefore, we can relate to quadrilateral NPBM as a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, NP equals to BM, but NP is 3. Therefore, BM must be also equal to 3 units in its length. likewise, according to the same rule, in rectangle NPBM, side PM equals to side, the opposite side NB, but PM is 3, therefore NB must be also equal to 3 units in its length. We can repeat on the same process here. So here we have actually found out that quadrilateral NPBM is not a rectangle but a square, because all of sides are equal to each other. Each of them is equal, each side equals to 3 units. If we repeat on the same process on this circle, we get here. We get here that this quadrilateral will be also a square, exactly like this. Is actually symmetric to each other, they are symmetric to each other, therefore we get here that we have here actually a square. And this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. Define this point as H. This angle must be equal to 90 degrees, and this angle must be also equal to 90 degrees according to rule number 1. The missing angle here must be equal to 90 degrees. All the sides of this square must be equal to each other. So we have here square HQ LD, all of its sides are equal to 3 units in its length, in their lengths. Okay, so in the next step we will extend the radius LQ by a straight line until it touches the side BC of the rectangle. The radius LQ is a radius that is absolutely a straight line. We extended the straight line LQ by a straight line, therefore the result must be a straight line. So here LT must be also a straight line. We define the touching point of the extended radius LQ and BC as T. So here LT must be also a straight line. Inside quadrilateral DLCT, inside this big quadrilateral DLCT, we have 1, 2, 3 rectangles, therefore the fourth angle must be also equal to 90 degrees. Therefore quadrilateral LDCT, that has 4 rectangles, we can relate to it as a rectangle. And you know that the opposite sides of a rectangle are equal to each other. That is to say, DL equals to TC, but DL is 3, therefore TC must be also equal to 3 units. In the next step, we will extend the radius NP of this circle until it touches side DC of the rectangle. The radius is a straight line. We extended the straight line NP by straight line, therefore the result must be also a straight line. We define the touching point of the extended radius NP inside DC as point J. So inside quadrilateral NBCJ we have 1, 2, 3 rectangles, therefore the fourth angle here must be also equal to 90 degrees. So quadrilateral NBCJ that has 4 right angles, we can relate to this quadrilateral as a rectangle. And you know that the opposite sides of a rectangle are equal to each other. That is to say, NB equals to JC. but NB is 3, therefore JC must be also equal to 3 units in its length. DC equals to 7 units, according to what is given us the question. So DC minus DH minus JC must be equal to the missing side HJ. Again, repeat again. DC is equal to 7 units minus DH minus JC must be equal to the missing side, that is HJ. So DC is 7 minus DH, that is 3, minus JC, that is also 3. So 7 minus 3 is 1. So found out that this missing side, JC, it is equals to 1 units in its length. This angle equals, DC is one straight line. This is a straight line, so if you focus on this side of the straight line, this is point J. Here the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at this side of the straight line, this is point J. We have this angle that is equal to 90 degrees, plus the missing angle here must be equal, in total they must be equal to 180 degrees. Therefore the missing angle here must be equal to 90 degrees. Likewise, LT is a straight line. If you focus on this side of the straight line LT at point Q, the sum of the angles must be equal to 180 degrees. So which angles we have at this side of the straight line LT at point Q? We have this angle is equal to 90 degrees, plus the missing angle in total must be equal to 180 degrees. Therefore the missing angle must be equal to 90 degrees. We define the intersection point here is F. So inside quadrangle QHJF we have 1, 2, 3 angles, therefore the fourth angle must be equal to 90 degrees. So inside quadrangle QHFJ we have 4 right angles, therefore can relate to quadrangle QHFJ as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say QH equals to FJ, but QH is 3, therefore FJ must be also equal to 3. According to the same rule, in a rectangle QHJF, HJ equals to QF. But HJ equals to 1, therefore QF must be also equal to 1 units in its length. We know that NJ is one straight line. If you focus on the upper side of the straight line NJ at point F, at the upper side of NJ at point F, the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of NJ at point F? We have this angle that is equal to 90 degrees, plus the missing angle, in total they must be equal to 180 degrees. Therefore the missing angle must be equal to 90 degrees. Okay. This angle must be equal to 90 degrees. So here BC is one straight line because it is one side of rectangle ABCD, therefore it is a straight line. If you focus on the upper side of the straight line BC at point T, here the sum of the angles must be equal to 180 degrees. So which angles we have at the upper side of BC at point T? We have this angle that is equal to 90 degrees, plus the missing angle, in total they must be equal to 180 degrees. Therefore the missing angle must be equal to 90 degrees. Likewise, if you focus on the upper side of the straight line NJ at point P, if you focus on the lower side of the straight line NJ at point P, and the sum of the angles must be equal to 180 degrees. So which angles we have at the lower side of NJ at point P? We have this angle is equal to 90 degrees, plus the missing angle in total must be equal to 180 degrees, therefore the missing angle must be equal to 90 degrees. So inside quadrangle PFTM we have 1, 2 flat angles, therefore the fourth angle must be equal to 90 degrees. So inside quadrangle PFMT we have 4 right angles, therefore quadrangle PFMT that has 4 right angles, we can relate to this quadrangle as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other, that is to say MT equals to PF. MT equals to PF, repeat again, in rectangle PFMT, MT equals to PF. So what is the length of MT? MT equals to BC, that is 24, minus TC, that is 3, minus BM, that is also 3. Therefore, MT in total equals to 24 minus 3 minus 3, that is actually 24 minus 6, that is 18. So MT equals to 18. So in rectangle PFMT, side MT must be equal to side PF according to the rule that the opposite sides of the rectangle are equal to each other. So MT equals to PF, but MT is 18, therefore PF must be also equal to 18 units in its length. Again, QF equals to 1 unit, PF equals to 18 units, and this angle equals to 90 degrees. Therefore, triangle QFP is a right angle. In the next step, we will implement the Pythagoras theorem of the right green triangle, triangle QFP. So I'll copy the right green triangle, triangle QFP, in a new page, and we will implement on this right green triangle, triangle QFP, the Pythagoras theorem. So actually, this is the right triangle QFP that I copied from the original drawing. Side PF equals to 18 units in itself. Side QF of this right triangle equals to 1 unit. The only missing side is the hypotenuse QP, that is the line segment that we are looking for. We have to find out the distance between the centers of the two circles, that is to say the length of line segment QP. So we implement the Pythagoras theorem in this right triangle, triangle QFP, in order to find out the length of the hypotenuse QP. And we get that according to the Pythagoras theorem in this right triangle QPF, QP square equals to QF square plus PF square. So QP square equals to QF square. QF is 1, therefore QF square is 1 square, that is 1, plus PF square. PF is 18, therefore PF square is 18 square, that is 324. So QP square, that is the square of the hypotenuse, that is the line segment that we are looking for, equals to 324 plus 1 is 325. Here we take a root out of this equation and we get that QP equals to the square root of 325. Actually, 325 is 25 times 13. So here we can take 25 out of the root. The square root of 25 is 5. So we get here 5 inside the root, we have only 13. We can already found out that the distance QP between the centers of those two circles is equals to either 5 times root of 13 units in terms of numbers, it is equal to 18.03 units. And that is the answer to our question. Okay, again, the distance between the centers of those two circles, that is to say the length of this line segment QP, it is equal to either 5 times root of 13 units, so in terms of numbers, it is equal to 18.03 units. So in the next step, I will summarize the lecture. In this lecture, we found out the distance between the centers of those two circles, that is to say, the length of this line segment QP. Q is the center of the circle, P is the center of the circle, and the distance between the centers is the length of this line segment QP. In addition, we know that those two circles are located inside rectangle ABCD. Side AB of the rectangle is equal to 7 units. The length of this rectangle BC is 24 units. Again, our mission is to find out the distance between the centers of those two circles, that is to say, the length of this line segment QP. So, first of all, because of the fact that ABC is a rectangle, all the 4 angles here are right angles. In addition, we know that the opposite sides of a rectangle are equal to each other. That is to say, side AB equals to side DC. But AB is 7, therefore DC is also 7. According to the sum rule, side BC of rectangle ABCD must be equal to side AD. But BC is 24, therefore AD must be also equal to 24 units in its length. Because of the fact that this angle ABC equals to 90 degrees, it means that triangle ABC is a right angle. So we can implement on this right angle ABC the Pythagoras theorem. So in the right angle ABC, by PT is a relation for Pythagoras theorem. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse on this right triangle ABC is AC, therefore the square of the hypotenuse is AC square. It must be equal to AB square plus BC square. Again, AC square equals to AB square plus BC square, according to the Pythagoras theorem. So AC square equals to AB square. AB is 7, therefore AB square is 7 squared, that is 49. Plus BC squared. BC is 24, therefore BC squared is 24 squared, that is 576. So in total, AC squared equals to 49 plus 576, that is actually 625. We took a root out of this equation and finally found out that AC equals to the square root of 625, that is actually 25. So AC, hypotenuse AC equals to 25 units in its length. Okay, so in the next step, I presented a new formula. Actually, we have here this circle that is blocked by the right triangle ABC. We want to find out a formula for the length of this radius. The radius of this circle is x according to our definition. We want to find out how to find out the length of the radius of this circle that is blocked by the right triangle ABC only by knowing the side lengths of the right triangle ABC that blocks this circle. Okay? So we have BC is tangent to this circle at point M. Point M is the point of tendency. Point O is the center of the circle. Point M is the point of the circle itself. Therefore, OM is the radius of this circle. The radius of M is drawn to point M, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. If BC is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. This angle equals to 90 degrees because we know that the triangle ABC is a right triangle. We join points, we define the point of tendency of tangent AB with this circle as N. We join points O and N together by a straight line. ON is the radius of this circle that is equal to X. The radius of ON is drawn to point X, that is the point of tendency of tangent AB with this circle. And whenever a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees, according to rule number 1. So inside quadrangle ONBM, we have 1, 2 right angles. Therefore, the fourth angle must be also equal to 90 degrees. According to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. So inside quadrangle NOBM, we have 4 right angles. Therefore, we can relate to quadrangle NOBM as a left angle. As we also know that the opposite sides of a left angle are equal to each other. That is to say, NO equals to BM, but NO is X, therefore BM must be also equal to X. According to the same rule that the opposite sides of left angle are equal to each other, we get that OM equals to NB, but OM is X, therefore NB must be also equal to X. So we found out finally that quadrangle NOBM is not a left angle but a square because all of its sides are equal to each other. Each of them is equal to X, that is the radius of this circle. Okay? So we know that NB is X, AB is A according to our definition, BC is B according to our definition, and the length of the opposite AC is C according to our definition. We just right now found out that NB is X, AB is A, and NB is X. So AB minus NB is AN. Again, AB minus NB is AN. So AN equals to AB that is A minus NB that is X. So in total, AN equals to A minus X. So here we have BC is B and BM is X. So BC minus BM is MC. So MC is BC minus BM. That is to say, MC is BC that is B minus BM that is X. So in total, MC equals to B minus X. So MC equals to B minus X and AN equals to A minus X. Then focus on the convex standpoint point A. From the convex standpoint point A, we have 2 tangents to this circle, tangent AN and tangent AS. And according to rule number 2, that the lengths of 2 tangents from a convex standpoint to a circle are equal, we'll get that AN must be equal to AS. But AN is A minus X, therefore AS must be also equal to A minus X. Likewise, according to the same rule number 2, if we focus on the convex standpoint point C, from the convex standpoint point C, we have 2 tangents to the circle, tangent CM and tangent CS. And according to rule number 2, they must be equal to each other. That is to say, CM equals to CS. But CM is B minus X, therefore CS must be also equal to B minus X. So the hypotenuse AC from one side it is equal to C according to our definition. But from the other side, the hypotenuse AC equals to AS plus SC. Again, the hypotenuse AC equals to AS plus SC. So you can write here that the length of the hypotenuse is C. But C also equals to AS plus SC. Yeah. C equals to AS plus SC. AS is A minus X and BX is AS is A minus X and BC is B minus X. So we can substitute AS by A minus X and SC by B minus X. So in total, C equals to A minus X plus B minus X. That is to say, C equals to A plus B minus X is minus 2X. So C equals to A plus B minus 2X. Subtracted 2X from this equation. And finally found out that actually we added 2X to this equation. We found out that 2X plus C equals to A plus B. We subtracted C from this equation and found out that 2X equals to A plus B minus C. Then we divided this equation by 2 and finally found out that X equals to A plus B minus C over 2. So we have here a general formula to find out the radius of any circle that is inscribed by right angle only by knowing the side lengths of the right angle that blocks the circle. That is to say, the radius will be equal to A plus B, that is the sum of the side lengths of the perpendiculars minus the length of the hypotenuse, that is C over 2. Now we can use the new formula. Here the radius of this circle will be equal to A plus B minus C over 2. Again, the radius of this circle X equals to A plus B minus C over 2. So we can use the new formula in order to find out the radius of this circle that we defined as R. Why? Because this circle is blocked by the right angle, triangle ABC. Therefore, the radius of this circle R, according to the new formula, will be equal to AB plus BC minus AC over 2. Repeat again, the radius of this circle that is blocked by the right angle ABC must be equal to, according to the new formula, to AB plus BC minus AC over 2. AB is 7, BC is 24, and the hypotenuse AC is 25. So it is 7 plus 25, that is 30. 7 plus 24, that is 31, minus 25 over 2. 31 minus 25 is 6, and 6 over 2 is 3. So finally we found out that the radius of this circle is 3 units. Then we found out, according to the same formula, the radius of this circle. We define the radius of this circle as X. According to the formula, the radius X must be equal to CD plus DA minus AC over 2. Is again the radius of the circle equals to CD plus AD minus CA over 2. CD is 7, AD is 24, minus CA, that is 25 over 2. 7 plus 24 is 31, 31 minus 25 is 6, and 6 over 2 is 3. So found out that the radius of this circle also equals to 3 units. Then we used rule number 1 that says that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here PM is the radius that is drawn to point M. That is the point of tendency. Therefore, tangent BC will be perpendicular to the radius MP. That is to say, this angle equals 90 degrees, this angle equals 90 degrees. We define the point of tendency of tangent AB with this circle as N. The radius Pn is drawn to point N, that is the point of tendency of tangent AB with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NP according to rule number 1. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So inside quadrilateral NPBM, inside this quadrilateral NPBM, we have 1, 2, 3 triangles, therefore the fourth angle must be equal to 90 degrees. So inside quadrilateral NPBM, we have 4 triangles, and therefore we can relate to this quadrilateral as a rectangle, and we also know that the opposite sides of a rectangle are equal to each other. That is to say, side NP equals to side BM. But NP equals to 3, therefore BM must be also equal to 3. According to the same rule, PM must be equal to NB. But PM is 3, therefore NB must be also equal to 3. So we actually found out that quadrilateral NPBM is not a rectangle but a square, because all of its sides are equal to each other. Each of them is equal to 3. So quadrangle NPBM is a rectangle. We can repeat on the same process here. It is symmetric, and we get that this quadrangle HQDL is also a square. All of its sides are equal to 3 units. So it is a square. Okay. Then we extended the radius NP by straight line until it touched the circle at point, until it touched side DC at point J. When you extend the straight line by straight line, the result is the straight line. So NJ is a straight line. In this way, we created quadrangle NBCJ. In this big quadrangle, we have 1, 2, 3 rectangles. Therefore, the fourth angle must be equal to 90 degrees. So inside quadrangle NBCJ, we have 4 rectangles. And therefore, we can relate to this quadrangle NBCJ as a rectangle. We know that the opposite sides of a rectangle are equal to each other. That is to say, NB equals to JC, but NB is 3, therefore JC is also 3. Okay. And then we extended the radius LQ by straight line until it touches the circle at point T. Therefore, we created quadrangle TCDL. Inside quadrangle DLTC, we have 1, 2, 3 rectangles. Therefore, the fourth angle must be also equal to 90 degrees. Okay. So here we have 1, 2 right angles, but here this angle also equals to 90 degrees because NJCB, it is also rectangle. So inside quadrangle FJCT, we have 1, 2, 3 rectangles. Therefore, the fourth angle must be also equal to 90 degrees. So quadrangle FJCT, that has 4 rectangles, we can relate to it as a rectangle. We also know that the opposite sides of a rectangle are equal to each other. That is to say, TC equals to FJ. But TC is 3, therefore FJ must be also equal to 3. So this angle equals to 90 degrees, and DC is a straight line, therefore this angle must be also equal to 90 degrees. Again, LT is a straight line, and this angle equals to 90 degrees, therefore the missing angle must be also equal to 90 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So those two angles are both equal to 90 degrees. According to the same rule, this angle equals to 90 degrees, therefore the missing angle must be also equal to 90 degrees. According to the same rule, this angle equals to 90 degrees, therefore the missing angle also equals to 90 degrees. So inside quadrangle QHJF, we have 4 rectangles. Therefore, quadrangle QHJF is a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, HJ equals to QF. What is the length of HJ? HJ equals to DC, that is 7, minus 3, minus 3. 7 minus 3 minus 3 is 1, so HJ equals to 1. And HJ equals to QF. But HJ is 1, therefore QF must be also equal to 1. QF equals to 1. And here, this angle equals to 90 degrees. Therefore, the missing angle must be equal to 90 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. NJ is a straight line. So if you focus on the upper side of the straight line NJ at point F, the sum of the angles must be equal to 180 degrees. So which angles we have? We have this angle is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. Therefore, the missing angle here must be equal to 90 degrees. Okay, this angle QFP equals to 90 degrees. Okay, now we have this angle equals to 90 degrees. Therefore, the missing angle must be equal to 90 degrees. This angle equals to 90 degrees. Therefore, the missing angle must be equal to 90 degrees. Likewise, if you focus on the lower side of the straight line NJ, at point F, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees. Likewise, if you focus on the upper side of the straight line BC at point T. This angle equals to 90 degrees, therefore the BC angle must be equal to 90 degrees. So we actually found out that in quadrangle PFTM we have 4 right angles, therefore quadrangle PFTM is a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, MT equals to PF. MT equals to PF. What is the length of MT? Here, MT equals to BC, that is 24, minus TC, that is 3, minus MB, that is 3. So in total, MT equals to 24 minus 3 minus 3, that is to say it is 24 minus 6, that is 18. So MT equals to 18 units in its length. And MPFT is a rectangle. That is to say MT equals to PF. But MT is 18, therefore PF must be also equal to 18 units. So then I copied the right rectangle PQF in a new page and implemented the Pythagoras theorem in this right triangle PQF. This is the right triangle PQF that I copied from the original drawing. PF is 18, PQF is 1. According to the Pythagoras theorem, PQ square equals to QF square plus PF square. So QP square equals to QF square. QF is 1, therefore QF square is 1 square, that is 1, plus PF square. PF is 18, therefore PF square is 18 squared, that is 324. So in conclusion, found out that QP square equals to 321 plus QP square equals to 324 plus 1 is 325. So QP square equals to 325. We took a root out of this equation and finally found out that QP, that is the line segment that we are looking for, equals to the square root of 325. But 325 is 25 times 13, so we can substitute 325 by 25 times 13. We did it. And the square root of 25 is 5. So we can take 25 out of the root, and inside the root we left only with 13. In conclusion, found out that the length of the hypotenuse QP is equal to either 5 times square root of 13 units, so in terms of numbers it is 18.03 units. The length of the hypotenuse QF, that is the distance between the centers of those two circles, is equal to either 5 times square root of 13 units, or in terms of numbers it is equal to 18.03 units. Okay, thank you very much.